High-quality chocolate is defined by its physical behavior, the clean snap, the glossy shine, and a melt that begins only when it touches the tongue. These traits are a byproduct of molecular physics. This behavior is the result of a specific thermodynamic coincidence. Cocoa butter, the primary fat in chocolate, melts at 35 degrees Celsius. That is exactly 1 degree below the average human body temperature. Because most of our daily environments sit around 20 degrees Celsius, chocolate remains a rigid solid on the shelf. It only surrenders that structure once it physically enters the warmth of our mouths. Making this material stable and shapeable requires a constant manipulation of its phase transitions. From the farm to the kitchen, chocolate is a study in controlling how a substance shifts between a liquid and a solid. Cacao begins as a delicate tropical fruit. To grow, it requires the consistent ambient heat of the tropics, usually between 25 and 30 degrees, and the protection of a dense, humid canopy. After harvest, the beans are piled for fermentation. The chemical reactions within these massive organic heaps are exothermic, causing the internal temperature to spike to 60 degrees. This heat is what develops the precursors for the chocolate's eventual flavor. Drying the beans stabilizes them, but the signature flavor isn't finalized until the beans undergo high-heat roasting. This step uses thermal energy to permanently lock in the chocolate's aromatic compounds. The roasted material then moves to industrial refiners. Here, heavy machinery applies both external heat and intense mechanical friction to crush the solids. This combination of force and temperature pushes the beans across the 35-degree threshold. The internal fats liquefy, transforming gritty particles into a smooth, flowing cocoa mass. Turning that hot liquid back into a stable solid requires overcoming a significant thermodynamic barrier. Simply cooling the mixture isn't enough to produce the material we recognize. Cocoa butter is polymorphic. It can solidify into several different crystal structures. Most of these arrangements are loose and disorganized, resulting in chocolate that is dull, crumbly, and prone to melting at room temperature. To achieve a stable result, chefs use a process called tempering. By cooling and agitating the chocolate, they force the fat molecules to form specific clusters, known as seed crystals or nuclei. This typically happens on a 20-degree marble slab. The chef spreads and moves the liquid, using the cool surface to kickstart the formation of those microscopic seeds. Then comes a final, counterintuitive step. The chocolate is slightly reheated. This targeted warmth is just high enough to melt away the weak, unstable crystals, leaving only the strongest, most heat-resistant lattice behind to grow. A tempered chocolate bar is a highly organized crystal lattice. It's specifically engineered to remain structurally stable until it meets the exact temperature of a human mouth. In the kitchen, pastry chefs exploit these thermal properties to push chocolate into new states. Textures like ganache and mousse require crossing back over the 35-degree melting point. This allows the fat-heavy chocolate to bond with water or dairy, creating a stable emulsion that can trap air as it cools. The molten chocolate cake is perhaps the most famous example of exploiting heat transfer and temperature gradients. By baking at an extreme 200 degrees, the exterior of the cake rapidly absorbs energy. The heat cooks the egg proteins and flour into a rigid sponge, creating a solid boundary. However, the timing is calibrated so that the core only reaches 38 degrees. This is just warm enough to keep the cocoa butter in its liquid phase, ensuring the center remains fluid while the outside is fully cooked. Chefs can also work at the opposite end of the thermal spectrum, using thermal shock. This involves spraying hot liquid chocolate droplets onto a surface that has been deep frozen to negative 18 degrees. This massive temperature drop forces instant crystal nucleation. It bypasses the slow steps of tempering to create a unique structural texture that looks and feels like velvet. The creation of chocolate is a study in material science, dependent on the control of crystal structures and phase transitions. Every step, from the heat of the tropical farm to the freezing shocks of high-end kitchens, is dictated by the narrow thermal window of cocoa butter. The next time a piece of chocolate melts on your tongue, you are feeling that engineering in real time. It is a phase transition, calibrated by nature and science to collapse at the exact temperature of the human body.